Right, our aim has been to apply the Adams-Moulton method to calculate the approximate value of, right, because you have to use the Adams-Chebyshev methods, but yeah, we are interested in the Adams-Moulton for purposes of our exam and assignments. To approximate solutions, we want to approximate the solutions to the following initial value problems. So we're given the initial value problems. The initial value in the first case is y0 is 1, and the next ones are given as well. Right, just to illustrate the idea, in each case, use the starting values obtained from the Numerical. So now, obviously, I looked at that, but my interest in giving this exercise has been to reinforce the Adams-Moulton method. Okay, so that is what we're going to reinforce today, and we're going to demonstrate how that method is supposed to be used. Okay, right. So how do we apply the Adams-Moulton methods to approximate the value of this particular function at different values? All right, so we begin as follows, right? We note that, right, to approximate the value of, or the values of y at t at different values, right, at different values. Right, so the values would be the values of y at any value. So I'm going to demonstrate that, but at 0.2, for instance, you could do that. At 0.3, the values of that, at 0.3, and this will go and so on. Right. And it actually obviously should go on up to the largest value here, and it should go on up to 1.0. 1.0. Now, what do we do here? First things first, we draw a table. So we construct a table of values. And now this table of values is always the case when they mention Adams-Moulton. Okay. Even when they mention the Adams-Chebyshev, but we are not really quite of interest for this particular module. So now we shall look at these particular entities here. So what is T? Right, so T now will have the specific values. So what do we start with? We start with the smallest value. So T starts from 0 to 1. So we shall start, say, to 2 decimal places. We shall start 0.0 to 1 decimal place. Right, and then now you have 0.1. Because H is 0.1. So the spacing is the step size is 0.1. And then we have 0.2. We have 0.3. But here today I just want to quite mention explicitly what had to be done here. And then you have 0.6, you have 0.7, you have 0.8, you have 0.9, and then you have 1.0. 1.0. Okay. Now, what then do we do? Right, so we continue. What do we then do? So we construct now. So now we get to the values of y. We get to the values of y, right? So what are the values of y? Now, we need to write next to this the values of y. For the purposes of our study, into how we study this. Right, so right, we continue. We continue. So now what do we then do here? We construct this and we make a couple of realizations. What is the value of the function, for instance, it's a given, what is y at 0? What would y at 0 be? Okay, so obviously there's a given initial value. And the initial value is this one. That at 0, the function is 1. So 1 decimal place, you can write it as 1.0. Okay, it's the initial value. And then now we need to approximate the rest of this, ideally. Okay, right. So how do we approximate? For instance, so we need to approximate, like I indicated. We need to
Hello.
Yes, please.
I think we did this
Yeah, we
last
did this.
lesson.
Yes, we did this. Yes, we went through this question briefly, but we did not write out the actual answers to it. But maybe the idea is clear. Is the idea clear, maybe?
Yes, it's clear.
Okay, thank you. That's fine if that's the case. Right. So now, what we're gonna do, thank you. We're gonna continue and look at question. I'll continue looking at the idea of what must be known for exam. The Chebyshev polynomials, with the Pade approximation. Okay, so it's very important, obviously, that you understand the Chebyshev polynomials with the Pade approximation for exam purposes, and we begin to discuss those right now. Okay, right. Right. So let's discuss the Pade approximation as it comes in the exam. And the Chebyshev polynomials. How these polynomials work and how these polynomials need to be studied. Okay. Right. Let's get started with the Chebyshev polynomials. Right. Here's a question as it comes in the exam. Right. The first three Chebyshev polynomials are these. Okay. So the question is clear. And you are given the first three Chebyshev polynomials. Okay, and now T0 is 1, T1 is x, T2 is 2x squared minus 1, T3 of x is 4x cubed minus 3x, and T4 is 8x to the fourth power minus 8x squared plus 1. Okay, so we have been given the first three polynomials, Chebyshev polynomials. The first question says we need to economize. We need to economize the truncated power series. This one. Right. So now we learn how to economize and to use the concept of economization. How do we economize? And we proceed to do so. Right. So to economize in part A, we begin as follows. Right. We note something that the given Chebyshev, in particular, the given truncated power series, first things first, is P a function of x, which is the same as 1 plus double x minus x cubed plus 3x to the fourth power. Okay, this is the given truncated power series. And we note the word truncated. The word truncated power series indicates that these power series are normally infinite. So now this one we have written fewer terms, and therefore it has been truncated or terminated. Right. So now what do we then do? Right. So we need to proceed as follows. We perform subtraction. So we subtract. Right. So we subtract. Right, so we subtract the following. Right. Now we subtract 3. Right, we subtract 3 over 4. Right, we subtract 3 over 4 of the fourth of T4 of x. Right, so if we multiply the T4 of x by actually 3 over 4, what do we get out of these? What do we get out of these? Right. So in other words, we're going to perform this subtraction. We take 3 over T4 of x, and we multiply by 3 over 4. And what that becomes is that you would have, at the end of the day, 3 to the 4th power. And then you'd have minus 3x to the 4th power. Right. And then you'd have minus 3x squared. And then you'd have plus 3 over 8. Right, so we actually subtract these from the truncated power series. And this subtraction is done basically in order to remove the highest. Okay, here's the reason for this. In order to remove the highest order, right, in order to remove the highest order term, right, and to obtain the economized, right, the economized series. Okay, this is going to become very clear soon. Right, economized series. Okay, right. And so, what does this mean for us? Right, so in other words, if you perform that subtraction, so you'd have the following. You'd have that the economized series now is g of x. Right, so you have subtracted from p of x. So in other words, you have p of x. Right, so if you take this p of x here, right, you take this p of x and you subtract from it 3 quarters of T4 of x. Right. Okay, you'll see what the objective of this is here. You'll see what the objective of this is here. I can move this further down. So in other words, what this signifies for us is that we have the polynomial g, which is p of x minus 3 quarters of T4 of x. Okay, you'll see exactly why this is the correct algebraic method to use. Okay, what is our p of x here? Okay, what is the truncated power series in the question? Right, the truncated power series is 1 plus 2x, etc. Okay, so we substitute that here. Right, so what is the truncated power series? We see that it is exactly 1 plus 2x. You'll see why this is the algebraic way to economize the series. You have the cube, and then you add 3x to the 4th power, and then you have this 3 quarters of that. Okay, you have 3 quarters of this. Okay, so we continue. All right, we continue. Right, so we have seen therefore that if we take the 4th T4 and then we actually subtract from p of x, we actually will have the we'll obtain this new economized polynomial. Okay, so let's just do the subtraction carefully and see what we are getting here. Right, so if we are saying that 3/4 of the T4 is basically the same as the following. It's basically the same as the following, right? So you have, you can put a minus here. Right, so we have already said this one here, 3⁴ minus 3x to the 4th power minus 3x squared plus, okay, we're seeing the algebra here, and we're going to simplify this as we perform the subtraction and see what result we get together. So that would be g of x is basically the same as. So if we subtract these, we subtract like terms, etc. We subtract like terms and so on. Right. So subtracting like terms, what does this give us? We have the constant 1, and we have minus 3⁴, which is exactly minus 81. And then we have plus, the plus 3/8. Okay, we're just going to be minus when multiplied out. So what will the constant term be? Can you analyze that? So we're going to write on the side here, if you have 1 minus 3⁴ minus 3/8. Okay, so these are the what are the constants, right? So if you add these constants, what do we obtain? Just a second, right? What do we obtain? So I want to test this here. So you have minus 3/8, minus 3/8 minus 81. Right, so you have exactly that one. Okay. You have exactly that one there. Okay, just one sec. I want to mention something about the actual algebra we use here. Right, the actual algebra we use here. What is the highest? Because I said ready. This is this thing we're doing here. The objective of this is to remove the highest order. The economy is to remove the highest order term. Right, so if we remove the highest order term, what is the highest order term? Well, the highest order in T4 is x to the 4th power. And then now, what is the highest order here? It is exactly 3⁴ power. And if our objective obviously is to remove that, we have already seen that we decide to perform the algebra. And we want to remove this. There are a couple of ways to do that. And we said, okay, if we take p to the power of p of x, and we subtract 3/4, this is what we get. This is exactly what we get. But does it really work that way? Right, so would need what? You'd need 3/8. Okay, you'd need 3/8. Okay, you'd need 3/8. Right, because if you have 3/8, then it's going to eliminate that. Right, just so let's do this. Because I'm following the guidelines in the material here. Right, so you need 3/8. I'm following the guidelines in the material. Sometimes, obviously, there are also sort of algebraic typos here. Right, so you'd need 3/8. Because I want to, yes, you need 3/8. So if you put 3/8 and you multiply that by 3/8, right, so you'd have therefore that this is going to be 3/8. Right, so the T4 is going to be, I'm going to write here, so it's going to be 8x to the 4th power minus 8x squared plus 1. Right. So sometimes there are also typos in the material we use. Right. So if you multiply through here, what does this give us? It gives us exactly 3x to the fourth power. And then what? Right. Okay. Minus. So it becomes 3x squared. And this becomes plus 3 over 8. 3 over 8. Right. So if it becomes therefore 3 out of 8. So you take this and you come here. And then now you'd have and like I said, sometimes the typos in the material we use. So you're gonna see how you economize that with 3 out of 8 here. And then this one here now, you have minus. And then what is 3 over 8? It's gonna become 3 to the fourth power. It's gonna obviously be able to eliminate the what? The highest order term. So you have this. Okay. Let's see what this gives us. Right, so we can expand the way we want. Right, so I'm going to expand quickly. So you have x cubed. Right, so plus 3x to the fourth power minus 3x to the fourth power. We can see that the highest order term is eliminated by this algebraic manipulation. So now that means that you have g of x is the same as. Right, so at this point, you can see that this one is out. Right, so if that is the case, what does this give us? Okay, we are in business and it looks like we're doing so well. In fact, we are doing very well. Right, so this is exactly the same as minus x cubed. We are done with the cubic term. And then we get to the quadratic term, which is plus 3x squared. Right, so we get to the plus 3x squared. Right, so we have 3x squared here. All right, and it's positive.
Hello.
Okay, yes, please.
How did you get 3 over 8?
Okay, that's a good question. How did I get 3 over 8? Right, I got 3 over 8 from the fact that we are looking at the two polynomials, and now we look at for the highest order term. What is the highest order term here? It is 3x to the fourth power in P of x in the targeted power series. But now in T4 of x, the highest order term is what? Is 8x to the fourth power. So we want to make the 8 3 in the T4 by multiplication. How can we make the coefficient 8 in the T4 to be the same as the coefficient 3 in the P of x targeted power series? So we multiply it by what? We multiply therefore by 3 out of 8. Okay, right. So and that is convenient because surely the highest order term here, which is 3x to the fourth power, is now eliminated by this algebraic manipulation. But moreover, we're able to see that we therefore have minus x cubed. Okay, then you have 3x to the fourth power, right? Eliminate, right? So we have 3x squared, right? So what else is left? Okay, we have a linear term, and the linear term is actually plus 2x. Right, plus 2x. And then we have two terms. So the 2x has been dealt with, so we're done with it. Then we have 1 minus 3 over 8. And 1 minus 3 over 8 is exactly what? It's exactly 5 over 8. This is good. This is good. So we have managed to economize the series. What does it mean to economize the series? Well, the objective is to remove the highest order term by taking the one of the share by share polynomials, and performing subtraction. You subtract the t multiplied by constant from the truncated power series. Okay, we're gonna see. So this one is the economized. This one is the economized series. Okay, so this g of x is the economized. Is the economized series. Right, is the economized series. Okay, how do we know it's the economized series? Well, because we can see that it is actually both the highest order terms in the truncated power series and the T4 have lost the highest order terms, which were the actual fourth power terms. They're both gone. So we're dealing with the cubic term, and the cubic term is certainly 1 degree less, and therefore we've managed to economize the series. Okay, right. Let's look at the next question. The next question says, here we need to give an upper limit for the absolute value of the difference between the original truncated power series and the economized one. Right? So these are exam questions, exam type questions. And now with mastering these exam type questions, we can be rest assured that passing is guaranteed. So now we're going to give an upper limit for the absolute value of the difference between the original truncated power series and the economized one. So we need to look at the original truncated power series and the economized one. But what do we do? Right, so we give an upper limit of the absolute value of the difference between the two. We proceed as follows. A Roman figure 2. A Roman figure 2. Right, so if we look at A Roman figure 2, we note that for all the share by share polynomials, Pi. Okay, so we are looking at arbitrary share by share polynomials Ti. We have that the modulus of Ti is less or equal to 1. Okay, note this. This is true for all share by share polynomials. We have that the modulus is less or equal to 1 for all the x which are elements of the interval, closed interval between -1 and 1. This is true for all share by share polynomials. It's a condition. And therefore, the difference the question is talking about. And therefore, the difference the question is talking about. What difference is the question talking about? The question is talking about the following difference. They're talking about the difference between the truncated power series and the economized one. Right, so the economized one is G and the truncated power series is P. And we find that the absolute value of the difference. And we have already seen that the absolute value of the difference is basically 3 out of 8 of T4 of x. Okay, so, and now if we get this here, by using the properties of the absolute value, this is going to be less or equal to 3 over 8. Okay, because the T over 4 the T4 modulus is less or equal to 1. Right, so and this here 3 over 8 is the same as 0.375 is a decimal fraction to 3 decimal places. Okay, right, so that is what we got, because they said just find the give the upper limit of the absolute value, and the upper limit of the absolute value is clearly this one. What is the upper limit of the absolute value? Is clearly that one. Okay, it's clearly 8 over 3 over 8. Okay, right. So we look at the next question. Now at this point, you need to be able to find the Pade approximation. Find a Pade approximation R4 of x with a denominator degree 2 to the function this one. Okay, let's look at this one. Right, so we are effectively saying we need to find the Pade approximation R4 of x with the denominator of degree 2 to the function that one. Right, so let's discuss the Pade approximation. What is the Pade approximation? Right, obviously now we're speaking about the denominator of degree 2. What does it mean? This one. Okay, so we look at B. We look at B. So the Pade approximation is given by, what is the Pade approximation that is of interest in this module? The Pade approximation is, they've already mentioned R4 of x. And this Pade approximation is basically A0 plus A1x plus A2x squared is divided by 1 plus B1x plus B2x squared. Okay, the Pade approximation R4 is given by this. And so obviously the condition has been very clear that you need a denominator of degree 2, so it's a polynomial of degree 2. And now this becomes the relation of the Pade approximation. I'm going to give more details about the general Pade approximation of a denominator of any degree. But what does this give us? So at this point, this gives in particular. So this gives, right? So this gives R4 of x minus the polynomial minus f. Because you were given f in the question. They said find a Pade approximation R4 of x with the denominator of degree 2 to the function this one. So the Pade approximation R4 to the function this. So you take R4, because the Pade approximation R4 to the function f, so you obtain the difference. And now, if this is the case, R4 minus that, so you'd have A0 plus A2 all right, so you divide by 1 plus B1x B2x squared. You subtract the polynomial f. But the polynomial f given the question is 4 plus, right, so the polynomial given the question is 4 plus 4x squared. It's 4 plus 4x squared minus 2x to the sixth power. So we add that one. We subtract it. Right, so we have 4 plus 4x squared. And then we subtract 2x to the sixth power. So which means it is a naught plus a1x plus a2x squared. So you have that 1 plus b1x plus b2x squared minus 4 minus 4x squared. And then you multiply minus and minus, it gives plus 2 x to the sixth power. Okay, right, that's what we get. What is the meaning of all this? What does this give? What do you obtain from this? Right, so we still remember that it is the Pade approximation R4, the formula for R4 we've already seen, and the polynomial f was given. So now, so we perform this subtraction, but which gives? Which gives? Right. We cross multiply these things. We cross multiply these things. Okay, we cross multiply these. Right. So if we cross multiply these, what does this give us? If we agree that this one is the approximate R4 is the approximation to F, and therefore the difference is identically 0. So it therefore gives 0 equals A1x. If R4 approximates, we've seen the formula for R4, but if it approximates F, then you'd have this. A1x, B2x squared. And then we have minus 4. Minus 4x squared. So what should we learn from this question? We need to observe the formula for the approximation, Pade approximation, the R4 with degree 2, because it corresponds to the 2 degrees in both the numerator and denominator are uniform, the same. Okay, right. So I want to mention, right, so we perform the algebraic manipulations here because we want to estimate exactly the R4 and want to get the explicit formula for R4. So we multiply out here, we do what we can, right? So we can do something. We can take across the 4 plus 4x squared plus 2x to the 6th power. Okay, I've taken these from the other side, making them positive. And then now you have a naught plus a1x plus a2x squared. You divide everything by 1 plus b1x plus b2x squared. Okay, so we equate these to 0 always when dealing with the Pade approximations. Right, we cross multiply this. So cross multiplying would give us exactly 4 plus 4x squared plus 2x to the 6th power. Okay, this is what we have on the left. But we multiply with b1x plus b2x squared. And then this is the same as a naught plus a1x plus a2. a2x squared. Okay, but the approximations are very examinable in the Ulysses indica. Okay, okay, we just need to multiply these out. Right, and now after multiplying this out, we group like terms and so on. So it's very clear, therefore, that we shall have the following. We shall have the following. Right, so if multiply out 4 by 1 is 4. Right, so that gives us the constant term and then plus. Then we also have 4b1x. And then next we have 4 b1 a3. And then we do x cubed. Four b2. Okay. And then now all right, so we're getting that. So is this multiplication? Let me see. 4b2 x, yeah. Yeah. And then what else are we getting? Okay, what else are we getting? Right, need to be obviously extra careful here that we're doing the multiplications correctly. Right, can I just do this because sometimes there are mistakes and this is just the algebra here. Need to just get the algebra right. Okay, right, let's just do the multiplication. So you have, let's do, right, so I'm gonna multiply by 4, so you have 4 plus 4b1x plus 4b2x squared. Okay, I multiply through by 4. Then next I multiply through by 4x squared, which means it is 4x squared plus 4, that's 4x squared by 1 is 4x squared. Then we have 4 b1 x cubed. Okay, good. We got that one. So multiplied by 4x squared, and we multiplied b1, and we get this one. And then next we multiply 4b2 x to the fourth power. 4b2 x to the fourth power. Right. And then what else do we get out of these? What else do we get out of these? We multiply 2x to the sixth power by 1. Right. So if you multiply 2x to the sixth power by 1, you have 2x to the sixth power. And then we multiply 2x to the sixth power by what? By b1. So it's 2b1 x to the seventh power. And then we have plus, we have 2b2 x to the what? To the eighth power. And this is equal to a naught plus a1x plus a2x squared. So now let's continue. Now what we do at this point, we group like terms. We group like terms on the left and like terms on the right. So on the left now, we should be very careful, give just a little bit more terms, but we shall get this done. So you'd have therefore that this is the only constant term. So the only constant term is 4 on the left. And then now the linear term is actually 4b1x, and it's the only one because there's no other x term on the left except on the right. Okay, and then now the quadratics. Right, so we have plus 4 into, okay, the quadratic terms on the left are 2, this and that. If you pull out 4, then you're going to be left with 1 plus b2, and then you have x squared. So we have those. The cubics, which is this one here, this cubic, and now what other cubic term is there? Let me check. Okay, let's check. What other cubic term is it? Okay, it's the only cubic term that exists. And let me see. The only cubic term that exists. Right, so if it's the only cubic term that exists, you note it down. So you have exactly 4b1. Let's write that one down. X cubed. Right, and then what else is there? Then we have the fourth order terms. 4b2. Fourth order. 4b2. Fourth order. Right, so, and then you have the rest of the things. Okay, 2x to the 6th power, and then 2b1, x to the 7th power, plus 2b2, x to the 8th power, x to the 8th power, and then this is the same as a naught plus a1x plus a2. Pade approximations is what we're discussing now. With the R4, R4 of x formula. Right, we shall discuss generalizations of the Pade approximation method. Right, so all right. Right. Right, so we continue. Right, so now if we continue, so we compare coefficients. Equate coefficients of like powers of x is the language we use. This module, and we say we equate coefficients of powers of x. Right, so let's equate. Right, if we do that, we equate to, okay, it's common practice to write this one, x to the all right, so you have x to the 4th power. So now x to the 4th power is gonna right, x to the 0th power. Right, x to the 0th power is the constant. So now we can say we have 4 equals the following. So 4 equals a naught. Right. Right, so we continue. Right, so we have x, the linear ones, x to the 1st power, and then that would be the same as what? That would be the same as the 4b1 is a1. Okay, so okay, now let's see this one here, the quadratic terms. Right, so the quadratic terms would be 4 into 1 plus b2. 4 into 1 plus b2 is equal to quadratic on the other side, a2. And then we continue the cubic terms. Right, so the cubic term would be this one, 4b1. So we write 4b1. 4b1 is equal to the cubic term on the other side is what? Is 0. The cubic term on the other side is 0. Because there's no cubic on the right side of the equation. Right. So now we have this one, the quartics, both order terms. Right. So you have a 4b2. Okay. For the quartic, 4b2 is the same as 0 because there's no fourth degree term on the other side, on the right. Okay, equate coefficients of like powers of x. After these, after equating them, we are able to make the observation that therefore the Pade approximation proceeds as follows. Right, it's the business we're discussing right now, and I'm going to generalize that. So therefore, right, so therefore B1, what is B1? Well, B1 is equal to 0 from the cubic. We just divide by 4, both left and right. And then here we have A naught. What is A naught? Right, A naught is equal to 4, exactly from the first equation of the constants, the x to the power naught terms. Right, so what else do we have? We have A1. What is A1? A1 is the same as A1 is the same as 0. Right. So A1 is the same as 0. Why is A1 the same as 0? Because A1, according to the linear terms, x to the power 1 terms, 4b1 is A1. 4b1 is A1, but b1 is 0, so A1 is also 0 by transitivity. Okay. Now we have b2. But b2, now we have that b2, this one, 4b2. Right, 4b2 is 0, which means dividing by 4 would mean b2 is 0. Okay, you'll see why we're getting all these things here. Why we're getting the b1s, the a naughts, the a1s, and the b2s. And then now we have something else. We have a2. Right, what is a2? a2 is 4 into 1 plus b2. But b2 is the same as what? It's naught. So which means that a2 is 4. Well, a2 is 4. Right. Okay, if we get all these things from these equations, we got of the x naught, x to the power 1, x to the power 2, until x to the fourth power, until all the quartics. What is the conclusion, therefore, is that thus we have R4 of x. What is R4 of x? What is R4 of x? R4 of x. What is it? This R4 of x. So R4 of x will be given by the following. Right. So it will be given by, right. We remember what we got earlier. We said R4 is A naught because the question said that denominator must be of degree 2. So it becomes A naught plus A1x. But yeah, I'm going to give a general description of the Pade approximation formula just when we're done with this one so that we can have a general view of this. And then we have A1x plus we have that A2x squared. We divide everything. We divide everything by 1 plus b1x, and then we have got everything now. Right, we have b2x squared. So what is a naught? It's 4. What is a1? A naught is 4. A1 is 0. So you can put here 0 into x because a1 is 0. And then we have a2. What is a2? We can see that a2 is exactly 4x squared because a2 is 4. We have already got it from the algebraic manipulation. Okay, so we are good. We continue right in the denominator. So we have 1 plus. What is b1? We have seen that b1 is naught, right? So we have naught x, naught x. And then what is b2? b2 is naught x squared. So this is only 1 because the 0x and the 0x squared vanish in the denominator. So we're dividing everything by 1. And if we do that, it's 4 plus 4x squared. Okay, now this is exactly the polynomial we're looking for in view of the Pade approximation. So which means that R4 of x, R subscript 4 of x is 4 plus 4x squared. And this is the Pade approximation of x, because find the Pade approximation R4. So this guy here, the R4, which is 4 plus that, is the Pade approximation they wanted, is the Pade approximation. Pade approximation to what? To f of x. Pade approximation to f of x. All right. Now we have got the Pade approximation to f of x, and we appear to be doing pretty well, and we are most certainly in business. But I want to mention something in passing, that as we speak about these Pade approximation, and we have found the Pade approximation to a sixth order polynomial, what is the general description of what we call the Pade approximation? And I think that it is very significant that we discuss these. Right, and we are here to make sure we discuss that, so that today evening we have a fair understanding of things, and we are able to make sense of the Pade approximation. Right, so we gonna discuss that just now here. Just now here, I'm apportioning time to discuss the idea of the Pade approximation there. Right, and the right. So, and here is the result. In general, how do we find the Pade approximation? And obviously it relates to series and the idea of what we call rational functions. Right. So we discuss this first. We discuss this first. We discuss what we call a rational function. Right, so a rational function R. Okay, this is basic. A rational function R of degree capital N has the form R of x, which is P of x divided by Q of x. Right, so a rational function of degree N has the form that. Okay, so I'm just describing the idea because we're going to use this in the general description of what we call the Pade approximation. of any order. So we have this, and this is true where the P of X and the Q of X are polynomials. Are polynomials whose degrees whose degrees sum, right? Whose degrees sum to n, right? Whose degrees sum to n. So it is a rational function of degree n. What is a rational function of degree n? So such a rational function has this particular expression, where the P and the Q are polynomials whose degrees sum to n. Right. So I want to mention the degrees summing to n and the significance of that in view of the Pade approximation. In view of the Pade approximation. But now let's look at Pade approximation statement. Pade approximation. Right, so in general, what do we mean by this? What do we mean by this in a general context? So by the Pade approximation, if we give a formal statement, we suppose R is a rational function. Rational function of degree the rational function of degree n, which equals n plus m. Okay, but right, by the approximation, generally, if we give a formal statement of that, and the kind of approximations we use in the formula R4 and its origins, right, we suppose R is a rational function of degree n, where n is small n plus small m, of the form, right, of the form P of x divided by Q of x, which is P naught, P1 plus Pn x to the nth power, which means Q naught, Q1. Okay, I want us to discuss this. Right, so we're just giving the general formula of the Pade approximation, and then you have that. Okay, so we are effectively saying, the Pade approximation, we suppose that R is a rational function of degree n, but when we speak about the degree of the rational function, we are speaking about the actual sum of the degrees. This is powerful, but it's very interesting because if you speak about the degree of a polynomial of quadratic nature, like your usual ax squared plus bx plus c, the degree is 2. But here, the degree of a rational polynomial, we note that it is n. When we call it n, where that is the sum of the degrees. So this Pade approximation, suppose R is a rational function of degree m and capital N, where it's the sum of the small n and capital and small m. Right, so that is the case. Okay, that is the case. That is the case. So this Pade approximation, I want to say something about it before we move on. Okay, I want to create a general notion here. This polynomial is actually the polynomial that used is used to approximate a function f on a closed interval. I'm looking at a little bit of theory now. On a closed interval I containing containing 0. For R to be defined as 0, I want to mention this, for R to be defined, right, to be defined at 0, right, for R to be defined at 0, requires right, for R to be defined as 0 requires that okay, it requires that Q naught be not 0. Okay, this is very important because you saw that in the example we did from the exam, from the exercise. Right. In fact, we make the following assumption. In fact, we can, and we always do, because we said that the denominator is of degree 2 in the question, and then what did that mean in a sense? We can assume that. Okay, we can assume that. We can assume that Q naught, the constant, is 1. We saw it was 1 in the previous. And for this is not the case. And for if this is not the case, we simply replace that. Okay. All right. So you saw we had Q1, just the Q naught here. We make it 1. We can assume that, and we always do. Now we go on to say, for if this is not the case, this is not the case. If it's not 1, that is, what does it mean? It's not the case. Right. If this is not the case, we simply replace p of x by p of x over Q naught. And Q of X by, okay, we'll try to make sense of this. QX over Q naught. Okay. Okay, I want us to discuss this just briefly. So the Pade approximation, that is a formula, is R of X, which is P over Q, where the P and Q are functions of X. It's used to approximate a function f on a closed interval containing 0. For R to be defined at 0 requires that Q naught be not 0. And in fact, we can assume that it is 1. For if it is not the case, we simply replace P of X by P of X over Q naught and Q of X by Q of X over Q naught. Okay, so we note that. All right, and then I want to give a bit more concrete examples on these so that we can make more sense of this as we move on. Right, so I want to give a nice small example. Two small examples. Okay, on the Pade. Okay, I don't want to spend a lot of time on these, but I think after these examples, then the Pade will be a very clear concept. Right, let's look at this one. Here is a very simple example. Besides that exam question we looked at, but we're trying to create a bit more general understanding. The Maclaurin. Maclaurin series expansion for e to the minus x is right. So it's done at first year, this one, first year calculus. I was just spending a bit more time on the Pade. Right, we're gonna move on, please, to another concept. Right, what is the Maclaurin series of the e to the minus x? Okay, we can find that one by using the Maclaurin series formula, like we did with the Taylor. But the difference between Taylor and Maclaurin is that Maclaurin is a series at 0. Right, about 0. About 0. So you have that this is minus 1 to the power I divided by I factorial, and it is the same as x to the power I, like this. So we then say find the Pade. Okay, it's a question, this example. First, we start with a question, for example. Find a Pade approximation to e to the power minus x of degree 5 with n equals 3 and m equals 2. Okay, let's look at the solution to this. Let's look at the solution to this. Right, so we have this. Then what is the solution to this? Find the Pade approximation to e to the minus x of degree 5 with n equals 3 and m equals 2. How do we solve this one? Okay, this is quite easy. Right. But we start by saying to actually find the Pade approximation, we need something. We need to choose P naught, P1, P2, P3, and then Q1. Okay, we are coming to understand this and what the meaning of all these things, the meanings of all these things are. And then Q2, for that, the coefficients. The coefficients of x to the power k for k equals naught, 1, 5 as 0 in the expression. Okay, we will understand what these words mean. Okay, we're going to solve now. Right, we're going to just perform some algebraic manipulations. Write the expression, this one here. Right, so we are saying to find the Pade approximation, we need to choose P0, P1, P2, P3, Q1, and Q2, so that the coefficients of x to the power k for k equals 0 to 5 or 0 in the expression. Okay, so you will understand what that means here. We did this in the previous example, so you're going to have this 1 minus x. Okay, this one is the Taylor. It's exactly this Maclaurin series written out in expanded form, not in sigma notation. So it's 1 minus x. Then you have x squared over 2. Then we have x cubed over 3 over 6. Right, and then it alternates because it's minus 1 to the I. Right, so you have that. Right, you have this now. And then you multiply this by the denominator. The denominator is, the Q naught is 1, because we do not want the denominator to become 0. So you have Q1x and plus Q2. It is consistent with the example we just did of the Pade approximation there, squared. And then now we subtract. Okay, this is just another way of doing the same thing where we just came from now. And then now, obviously, you'd have the P naught. Okay, what is the degree of this one? You will just see now. P1, and then you have P2 x squared plus P3 x cubed. Okay, so we have this. And then now we then say, um, we have this. And then we continue to say expanding. Okay, you'll understand what this or what all these things mean. Right, so expanding. Right, so expanding and collecting terms produces. Expanding and collecting terms produces. Okay, so I'm going to be very brief here. Okay, you can spend a lot of time on this per day. In particular, this example is not a very um, complicated example, so it's a very basic example in the per day. The next example it's very important for exam purposes. So you'd have x to the power 5, for example. You'd have that if you expand everything and you add all the terms up, so it's going to be x to the power 5 is going to be minus 1 over 20 plus 1 over 24 q1 minus 1 over 6 q2 is equal to 0. And then you have x, this one, which is 1 over 2 minus q1 plus q2, which is equal to q2. And then you have x to the fourth power. We're comparing expanding and collecting terms produces x to the fourth power. This one is going to be 1 out of 24. Right, so it's going to be 1 out of 24. Okay, minus 1 over 6 p1 plus 1/2 equals, okay, I need to say here, right, so this one here is exactly minus 1/6. Okay, I need to change this one. Right, I need to change these here. Let's write the correct things here. So you have 1/24 and then minus 1 over 6 q1. But I'm just speaking about the per day, please. It's not that I'm just speaking about the p's and the q's here. 1/2 q2 equals naught. And then there's also x cubed. We compare the x cubed terms. Yeah, expanding and collecting the terms. We're just collecting the terms. Right, so you have this one for the collecting the x cubed terms, the coefficients, the coefficient of the x cubed will be like this. Okay, just that it's a bit laborious to go through the rest of this expansion. But now we can just summarize like this and then say it is P3 here. And then here there is x1, right? So this is that minus 1 plus q1. This one is equal to p1. And then this one is x naught. Okay, the constants would be the same as 1 is the same as p naught. Okay, so we have this. So we said just expanding and collecting the terms, this is what we get. This is what we get. Okay. Okay. So what is the meaning of these? What is the meaning of these? Right. So the meaning of this would be the meaning of these would be solving these systems. Come back to that. Solving right. So solving the system. We formed a system, but solving the system gives P1. What is P1? Okay, if we solve everything, it's going to be P1 equals minus 3 or 5. No, it can be very easy, but I'm just writing the results. And then if you solve this is a system of we can form matrices of this out of this. These are linear equations. So you can even use MATLAB to do this, but yeah, there's no need to use MATLAB. You can just do this because you have fewer variables. So you have that P2 is 3 out of 20, and then P3, which is minus 1 over 60. And then Q1 is 2 out of 5. Is 2 out of 5. And then we have Q2 is equal to 1 out of 20. Right. With this being said here, okay, I'm gonna give more information about this. Okay, there's more information to give. Okay, just pondering as well as we go through this solution. Right. So this observation means that to solve the Pade approximation itself. Okay, this is one example, and then I'm going to give another example, and then okay, just give another solid example. So this one is too basic. But so the Pade approximation is right. So it is R of X. Okay, we have seen that the Pade approximation itself is given by Px over Q of X. That is the formula. But the P itself is the same as what? Is P naught plus P1x plus P2x squared plus P3x cubed. What is Q of X? Okay, so this one, we take it to be 1 plus, we always take it, this one, we make the choice of the Q naught, 1 Q. Apologies, I lost you someone, it appears. Okay, So that at the end of the day, this one is the same as what?
No.
Okay, okay, that's fine. I think I lost you, but yeah, yeah, it's okay because this is being recorded. So it's being recorded, so you're gonna get the discussion here. On the q of x, which is 1 plus. Okay, now this. Okay, obviously we agree that this for the Pade approximation, the q of x is the same as what? Right, the q of x is the same as q naught q1 x plus q2 x squared. Right, so but the q naught we always choose it to be 1 to avoid the denominator being 0. So therefore we have only q1x and then we have q2x squared. Okay, look at this now. Because the, the we from the question we were told that m must be 2 and n must be what? N must be 3. Okay, so we understand therefore that at this point what we're having is that the the m and the n is for the n is for the top. Right, so the n is for the top and the m is for the bottom. So you can see the m is 2, but this equals. Right, so what is p naught and everything? What is p1? So we'll see that this is 1 minus p1x. The p1 is actually minus 3 out of 5. Okay, we're just dealing with the Pade here. Okay, it's not really a big deal, but now it comes normally with the Chebyshev polynomials. And I want to just discuss the Chebyshev polynomials as well. Right, so it is 1 minus 3 over 5 and then plus 3 out of 20 x squared minus 1 out of 60 minus 1 out of 60 x cubed. Right, it is divided by, okay, the denominator is always 1 there. And then plus q1 itself. What is q1 itself? q of 5. q of 5x plus 1 over 20x squared. Right, so this is going to be the Pade approximation. What kind of a Pade approximation is this? Well, it is the Pade approximation to the following thing. Right, so it is certainly the Pade approximation is the Pade approximation to something. Okay, to what? It is a Pade approximation to, always say is a Pade approximation to e to the power, minus x. Is a Pade approximation to e to the power minus x. Okay, to e to the power minus x of degree. Okay, of degree 5. The degree is 5 because it is the sum of the degrees. 2 plus 3, which is 5. So, yeah. Okay. I want to mention something here. There's a little bit of theory that you need to sort of understand. Right. We can then express the coefficient of that compactly as that. Then the rational function paradox results from the linear expansions and so on. Okay, right. We need to mention that. So I want to mention in passing that we have the following. I want to mention in passing. All right. Oh, okay. I want to mention in passing something. Right. Okay. This is just okay. this Pade approximation has a bit of theory behind, but what kind of theory? We saw that when I was here, this can look strange a little bit, but it's very important to bring to give a context to this. And the context is this. When you have what we had here was nothing other than what? Right, it was nothing other than the okay. I'm glad it did not shut down. Right, so you'd have K, the summation, R equals naught, A I Q K minus I, this summation, right, this summation, right. So you have this summation there, and then you subtract from it TK, TK. Right, so you have that. But obviously this is like K minus I here. Right. Okay. It's exactly, we're drawing a one-to-one relation between the this expression, which helps us to determine the Pade approximation, but also we are able to see that this summation I equals naught to K, A subscript I, Q K minus I is PK, okay, where K at the top of the summation sign is 0, 1 up to N. Okay, I'm mentioning this because we draw a one-to-one relation from the fact that if we have this here, this summation is actually equal to 0. This summation is equal to 0. But there's a tendency of just writing the summation like the way we did. And now the understanding is that it is equal to 0 because we can transpose the p's, the p0 and so on, and so that now we have the pk on the right. Okay. What is the meaning of all these? Well, this is very, very important because it brings us to something called the Chebyshev polynomials. The Chebyshev polynomials. What are these Chebyshev polynomials? Okay, I want us to discuss them as well. These Chebyshev polynomials, what are they? First things first. Right. First things first, I want to speak about this. See if I can get a good example here. Very good example, very good example, very good example. Determine all degree 3 Pade approximations of that, compare with that result and that. Right, determine the Pade. Okay, I'm going to write the things down, the things I'm thinking, I'm seeing here. Okay. I'm going to write the things on the screen. Right, so you have that. The first 5 terms of the Chebyshev polynomials are that, expansion of that. Determine the Chebyshev rational approximation of degree 5 with n equals 3 and m equals 2. Okay, you're going to see what that means just now here. Okay. Right, you're going to see what that means just now here. Right. So I'm gonna see what that means. But now, all right. Thinking lot here. Right. Right. All right, we normally do the per day, but now I want to speak about the Chebyshev racial function approximation. But obviously, that one is not quite examinable. So I want to speak about things that are very important, so that are examinable, not things that are going to waste our time here, and discussing things that are not are not significant to us here. Right. So we're good. Um, right, we're good. Right, I want to see something. Okay, I think that I've spoken a little bit more about these per day approximations. I want to now highlight something about the famous concept we have studied. What is the famous concept that we have studied? The famous concept we have studied is the concept of right, is the concept of right. So the famous concept we have studied is the concept of the Adams-Moulton method. So I would like us to discuss the Adams-Moulton method. We discussed it, but um, in comparison with the analytical solution, it's significant that we um, look at a different case study. For example, if one looks at this question and now um, in the analytical solution and the computer algorithm associated with this, right? The differential equation, that one that is given there, is what? Right. So we note the differential equation that is given. Here's the differential equation that is given, this one, and you have that. So starting values are these. Use the fourth order Adams-Moulton predictor correct method with h equals 0.2 to solve the equation up to 1, 2. Compare with the analytical solution, this one. Okay, I want to compare with the analytical solution here. So how do we solve this one, this question? How do we solve this? We note that first things first, given y primed, which is y minus x squared. Okay, that is a differential equation that is given. And a couple of initial values have been given, like your y naught is 1. You have also been given that y of 0.2 is 1.2186. You've been given that y of 0.4. Y of 0.4 is 1.4682. Y of 0 0.6, 1.73. So done. Okay, these are just the given initial values. This one, that one, and that one. Okay, right. So what is the analytical solution of this? So we need to compare with the analytical solution that one. Okay, so yeah, um, the analytical solution. What is the analytical solution? So we look at the differential equation dy dx, just y primed, and it can be written as dy dx, y primed, and then you subtract y, but you subtract y, and then you equate it to minus x squared. Okay, this is just, normally these differential equations can be solved by using the usual methods in calculus. So this one is first order differential equation. So it is of the form, y primed plus px y is equal to qx. Okay, normally this is done in first day calculus, and this differential equation can be written like this in the form p and q. But we note therefore that our p is what? Is -1, and our q is minus x squared. Okay. Now the integrating factor, is there's something called integrating factor. So we just recap on that one. Okay. It is e to the integral of p of x dx, which is the same as e to the integral of the p, which is minus dx, e to the minus x. And then we have that. And then now, when we got this, what do we do with this? We take the integrating factor, we multiply both sides of the differential equation. Right, the differential equation itself given is like y primed minus y is equal to minus x squared. So if we multiply by e to the minus, so it is y primed e to the minus x minus e minus e. Okay, I multiplied by the integrating factor. We just got both sides of the given differential equation. We just want just showing how to solve this differential equation. It's not really a big deal in this course because that's mostly done in first year. Right. So with that, we are able to do the next thing. What do we do next? Um we do anything possible to solve this equation. What do we do to solve this particular equation? Okay, can be a couple of typos here. Right. So what we do here is we want to integrate. Right. So to integrate, so we can write this as this. E to the minus x equals y e to the minus x minus x squared e to the minus x. Or um this one is the same as dy dx. Okay, dy dx is the same as y primed, which is y e to the minus x minus x squared e to the minus x. So which means dy e to the minus x. So you can write e to the minus x squared e to the minus x dx. At what point then you can integrate both left and right? If you integrate both left and right, we have y e to the minus x. Right, so if you have that, what does this give us? Right, you'd have the integral of y e to the minus x dx minus the integral of x squared e to the minus x dx. Right, so what is this? Right, what is this? So, we're able to see what this is here. We're able to see exactly what this is here. Okay. At this point, we integrate. We can add a constant, but yeah, we can add a couple of constants. The fact that we've already integrated here, and you got y e to the minus x, and then you integrate the other one. Right. So if you integrate the other one by integration by parts, so using integration by parts, okay, as I said, that this is not a big deal, the method of solving differential equations. It's just that for the analytical solution part, it's significant to show that using integration by parts, we are able to achieve that y e to the minus x becomes the same as x squared e to the minus x plus 2x e to the minus x plus 2x e to the minus x. Let's see. Now you take an initial value and be able to see what that is. Like one at y0. The initial value is that y0 is what? Y0 is 1. Okay, this is just the analytical solution part component where we're just manipulating the using calculus techniques. And then now you're saying y0 is 1, x and y. So, which means now you can substitute everything and say y is 1, x is 0. And then x is 0 squared e to the minus 0. 0, 0x, 0x plus c. And then we need to get the constant c, which means you have 1 is 0, 0 plus 2 plus c, which means c is minus 1. Right, having obtained c to be minus 1, which means therefore we can be able to write the following here. We can rewrite that x squared plus 2x plus 2 minus e to the x is the answer. Something called the numerical solution to this. Okay, so the numerical solution. We were looking at the analytical solution, but what is the numerical solution? Right, we note that the numerical solution is um, anchored and justified by the fact that these Adams-Moulton method is a multi-step method that is more than one past value is used to approximate the new value. All right. Right. So now I want to mention that number one, there's something we call the third order. The third order Adams method. The third order Adams method. Okay. The third order Adams method has a local. It has a local error. Error of order. Of order 4. And a global. And a global error of order 3. yi plus 1 is equal to? Okay, the third order is yi plus 1 is equal to yi. Just discussing these formulas here. And then obviously h over 1223 fi minus 16 fi minus 1 plus 5 fi minus 2, where fi means fi. So the third order Adams method has a local error of order 4 and a global error of order 3. Okay, so, and the formula is that yi plus 1 is equal to yi, etc. That. And then I want us to discuss the fourth order, because that is the most popular. We did the fourth order last time because it was given the exam. This is the third order formula. But the fourth order formula for the Adams what? Adams-Moulton method. The fourth order. Okay, you're gonna master this module anyway. Obviously we're just covering some of these, but yeah, it's very important that at the end of the day, you pass this. You're gonna pass this module anyway. Okay, so the fourth order Adams. You know that sometimes it's like, why are we doing all these? And what's, I mean, we pass with this? Yes. Right. So Adams method, okay, is the most popular because we did that. Right. But the fourth order Adams method is also called, another name for it, also called the Adams Besh. Um Besh fourth method. Right. The fourth order Adams method would also called the is yi plus 1. Which is only yi plus h over 24 into 55. Right. Okay, it's plus 55. Okay, this one we did last time. We did last time, but we're looking at it again. Okay, the fourth order, we're just recapping the formula there. Okay, the fourth order, which is also called the Adams-Bashforth method, is the one that has the 55 in it, and there's h over 24, 55 fi. These formulas will always be, where necessary, often given, but it's very important to note them just in case they don't give them out. 55 fi minus 59 if they mention the fourth order Adams method. Right, so you have this one. Um, 55 fi minus 59 fi minus 1. Plus 37 plus 37 fi minus 2. Right, minus 9 fi minus 3. All right. Okay, this is the fourth order Adams method, and that is the formula. Something very important that you need to learn and that you need to know as well is the Milner method. That is number 3. Right, Milner's predictor. Predictor corrector method. Milner's predictor corrector method. Okay, it's very important that you learn the formulas as well. Okay, we used something similar for the Adams-Moulton, but yeah, Milner's predictor corrector method is yp equals 4h over 3 into twice fi minus fi minus 1 plus double fi minus 2 close plus yi minus 3 yi plus 1 subscript equals yi minus 1 plus h over 3 into f xi plus h, and then y subscript p plus right, so 4 subscript 4 fi plus fi minus 1. So you have that. Okay, so this is the Milner's predictor corrector method. Predictor corrector. So the first one is the predictor and then the corrector. Okay, I'm mentioning these the numerical methods here. Okay. Right. The next thing we're going to learn, number 4, is the fourth one. The fourth one. Right. The fourth one. Right. So the fourth thing that we're going to do is the following. Right. So the fourth thing that we're going to do is the following, and it's called the most popular we've learned, not just the Adams fourth order, but the Adams-Moulton. The Adams-Moulton method. Okay, the Adams-Moulton method has famous names, but it is also called it's also called the Adams predictor corrector. Predictor corrector method. For now, the Adams-Moulton and also called the Adams predictor corrector, we saw that in one previous discussion we had, but yeah, we can just write out the formula because we need to just conclude this particular exam question or exercise. Yp is yi plus h over 24. This is the famous Adams-Moulton, also called the Adams predictor corrector, Adams-Moulton. So it's h over 24, but we know that this is 55. Fi minus 59 Fi, okay, and then plus 37 plus 37 Fi minus 2 minus 9 Fi minus 3 y I plus 1 yi plus h over 24 9 f into xi plus h yp plus 19 fi minus 5 fi minus 1 plus fi minus 2. Okay, these two formulas are we called them the Adams predictor corrector, and then they're also called the Adams-Moulton method formulas. Right, so right, so what is important about this? What is important about this? Okay, we must make sure. So what is important about these formulas? What is particularly important about them? So what is important is what I'm going to state now. And we must make sure we must make sure we must make sure that we can produce the table of results by This is very important. By using a calculator. Right. So we must make sure that we can produce a table of results by using a calculator. Okay. The Adams-Moulton method was used before. For age equals 0.2 in this exercise, we have that AX is starting at 0.6. We are continuing from 0.6, then we have 0.8. We add that one. Right. We add and then you have 1.20. Um, okay. Then you would have the values of y. The values of y. Okay, we use the predictions. 1.73, 79, 3.0145. Okay, this was done in the previous discussion, but I'm just highlighting because it came in this assessment. 3.28, 3.28, 17, 3.5199. And then we deal with the exact y. 1.7379, 2.0145. Here they coincide. It's not always the case that the exact and the y coincide. Okay, but here they do coincide. Okay, I'm gonna yeah, we did this, but yeah, I'm gonna elaborate much on this. 25199. Okay, this is the exact y, and then now you have the error because they coincide. The error is 0 because the exact y and the y are exactly the same, so the area is 0 with quadruple to 4 decimal places. And then here you get minus 0, and then here you get minus 0, and here you get minus 0. Right, so you have fxy. Right, we saw that we defined this one is the differential equation. Okay, if we substitute everything, the x and the y into the differential equation, we get 1.3779. We get 2.28. This is the table. You must be able to produce this table with a calculator from because in the exam, we use a calculator. Okay, but this one is less. It's just, in the exam, there's no computer algorithm that is going to be used. Okay, so it's very important that one is able to just use exactly this calculator, use a calculator. Right, so I was then saying now you can clean this up. And clean this up here. Right, and then come here. So now this one is 1.3745, and this one is 1.2817. Okay, I want to discuss this briefly. The predictor values using the predictor formula, they are 0, 1, 4, 6. Just a summary of all the values, but you need to get them step by step. With a calculator, 2.2819, and then 2.5202. And then f of x plus h, yp. 1.3746. 1.2819. And then 1.0802. So you have exactly these values, which are the approximations that are required for this, because the question said use the fourth order Adams-Moulton predictor corrector method with h equals 0.2 to solve the equation up to x equal to 1.2. But we understand that we start from 0. But some of these are already known. Okay, you draw the table. The table has the values. Has the values of, and start from n. You start with n, you can write. Right, so you have a couple of values that are involved there. Right, so you have a couple of values that are involved in this one. Right, so the values that are involved, you see therefore that you just were determining others. I want to mention that you'd have like x. Okay, we have these values, but I want to mention something else. Right, so you'd realize that in this case, when the problem is given like this, how do we draw the table? Just I want to mention this. You realize that x is there. Right, so you realize that x is there. And to pick a different color here. Okay, so you realize that x is there, for example. And now x is 0.2, 0.4, 0.6. Okay, you have 0.6. And then you have y. What is y at 0.6? Is this one. Is 1.7379. Okay, we're just constructing the table. And then we do 0.8. We do, because h is 0.2. So we move instead of 0.2, we add 0.2 here. It becomes 1.0. And then we add 0.2, it becomes 1.2. So obviously we go up to 1.2. And then now we do the rest of this. Obviously, we can see that others are not given, like the 0.8. So we need to get the y at 0.8, etc. Okay, right. And now the y at 0.8, how do you get the y at 0.8? we've seen that the y 0.8, you use the previous one to consider because you already have 0.6, you can get this 0.8. Let's practice. Okay, I'm just gonna get one because I'm sure that time is gone a lot. Okay, um, I'm just gonna get one. All right, I'm just gonna get one here. I'm just gonna get one because time is really gone, gone, gone. Right, time is gone. Right, so for example, because we're supposed to use the Adams-Moulton, also called the Adams predictor corrector. Right, so we have the predictor and the corrector. So for example, um, we can get y something. Right, so I want to just practice with you now this one here. Okay, we need to have this. Let's look at y I plus 1. And then now y I plus 1 is, I want to get y at the next value. So y at the next value is y what? Right, I what? Right, so you'd have to remember something. I'll start here. So you would start x is 0, 0.0, 0, 0.2, 0, 0.4, 0, 0.6, 0, 0.8, 1.0, and then 1.2. So the values of n here. Right, so the values of n that we note, right, so those values of n that we note are values of n that are extremely, extremely important for us. Right, so just note that. We need to finish, we're finishing, please. It's not that we are doing anything. Right, so n, the values of n will be 1 here, and then this one will be 2, and then this one will be 3. Mhm. And this one will be 4, 5, 6, 7, something like that. Okay, we're starting from 0 to 1.2. Right, so yeah, 1.2 is at 7. Okay, so I'm finishing now. I'm just practicing just to get a value like this one. So now, what is the meaning of this? So we're gonna say at t equals at t equals something. Okay, rounding up for this question. So at t equals, we want to do is at t equals 0.8. So we're gonna have at 0.8 we have 5. We have 5 and 5. Right, so we have n equals 5. So it is n equals 5, so you can call it y5. But y5 is going to be at 1 less. So it's going to be at y4 plus h over 24. And then 9f. Right, so x4 plus h, yp. So we need the predictor. Right. This is gonna drag a little bit, so I think that I'm just gonna leave it. I'm just gonna comment on it. Okay, this is 4 minus 5 f. Right. So you have that this one is gonna be what? It's gonna be 3, and this one is gonna be 2. Okay, but now we have this. Right? It's very interesting. Right. And then what is y4? Y4, we already have it at n equals 4. It's exactly the one above. Is the one above. Right. So if it is the one above, y4 is already there. And then x4 is exactly that one. H, yp. Yp is the predictor. And so the predictor can be obtained there. Okay. All right. For time's sake, I think that I'm just gonna say I'm gonna make a comment much about this in my next discussion. Right. But why all these formulas? Okay. This you're gonna see, but I see even the program is a little bit tired here because it's not. Sometimes it's blanking up. But yeah, I was speaking about the methods. So I'll just say in summary. Right. In summary, you have the Adams method and the Adams fourth order. The fourth order Adams method is also called Adams-Bashforth. Is that one? Milner's predictor corrector is actually this one here. And Adams-Moulton, also called the Adams predictor corrector, others. So just you need to note these things, and we shall continue with other methods like your shooting method and your in detail the Runge-Kutta methods. In detail the Runge-Kutta methods with the Euler, the Euler methods as well. The couple several Euler methods like the simple Euler and so on. Right. So we shall discuss those as well in my next appearance. And a bit more examinable methods that you need to learn, and a bit more exam hints. Right. When are we going to meet again? That becomes a question. I've indicated that I suggested that we hold our meetings every Thursday at 8 p.m., but we can meet on other days as well. Because we lost time, I'm proposing that we meet on Monday 8 p.m. You think about it, please. I'm hoping ESCOM is not going to let us down. Monday, 8 p.m. We're going to do more numerical methods. And I'm looking at how we shall master the course. I'm sure that at the end of what is question, we shall be very, very perfect when it comes to solving problems involving numerical methods and the rest of the methods. Yeah, but thanks a lot then for joining us, Saman, and have a good evening. I'll see you then
Can
Monday.
we
Yes,
can
please.
we change the time if it's possible?
Yes, we can change the time. Yeah.
Uh,
What time do you prefer? Obviously, I need to hear from you.
1 o'clock.
Okay, 1 o'clock is perfect. Okay. Right. So 1 o'clock is
And
perfect. So please
can we
come
do
again.
can we do Taylor series expansion for our next lesson? One question.
Yeah, perfect. We shall do that. Okay. Very interesting. Right. So yeah, because I proposed that we meet on Monday. So so you're thinking Monday 1 p.m. is okay?
Yes.
All right. That's fine. So that's okay. I'll see you then Monday 1 p.m. But that does not mean that we cannot meet on the usual Thursday. Yeah. Okay. Yeah. That's fine. I'll see you then Monday 1 p.m. and then we'll talk. Okay. But yeah, I'm gonna pause this video in the next couple of minutes. 30 minutes or something, I'm sure it will be loaded. So that you can maybe just pass through and see exactly what was happening. But yeah, but thanks a lot and have a good evening, Saman. Okay. Okay, thanks then. And goodbye.